Good morning to everyone. This is Dr. B. Polaiah, working as a professor in the Department of IT, Institute of Aeronautical Engineering, Hyderabad. I am very glad to inform you that is today we are going to have the video lecture, which is we simply call ELRV video, which we can see this towards the understanding on definition and terminology on image enhancement and basics of spatial filter. So what do you want to understand from here? You are going to have that information about simple definition and its terminology, how we may elaborately know. That's what we are going to concentrate today. So we are going to understand from today onwards about this definition and terminology, which we are going to be understand. I'm very happy to inform you that once again I'm very happy to say that wish you all very good morning. Let us be going to start our definition and terminology on image enhancement and the basics of spatial filtering. So what do you mean this image enhancement, especially in spatial domain? So we are going to have this understanding about defined spatial domain. Usually we used to consider that the section of the real plane scanned by the coordinates of an image is called the spatial domain. That is simply a image which we are going to have. This is the image, okay, either 2D or 3D image. This image right now we are keeping into the to understand in a spatial domain, that is called Cartesian coordinates. That is coordinates of an image is called a spatial domain. So once we understand the simple definition of a spatial domain, let us to represent in the form of 2D matrix, where each element of the matrix represents pixel intensity. This state of 2D matrices that depicted the intensity distribution of an image is called spatial domain, where this grayscale image, which we are going to be keeping in terms of the meaning of grayscale image is black and white image. Black and white image. This is called black and white image. We represent into the 2D matrix, which is right now we are keeping in terms of your values, that is pixel intensity values. Okay. So that values we are going to be keep in terms of number of rows and number of columns. Here number of columns are 2. Number of rows are 1, 2, 3, 4, 5, 6, 7, 8, 9. So we are going to have that 2D, that is a matrix formation. Whereas if you want to see this enhancement technique, specify the objective of an image enhancement technique is nothing but the objective of enhancement technique is to process an image so that the result is more suitable than the original image for a particular application, which we going to keep in terms of two categorization of the in image enhancement. What do you mean this? We are defining such a two categories of image enhancement is number one, direct manipulation of picture image. Number two, the frequency domain methods based on modifying the image by Fourier transformation. By using these two categories, we are going to concentration on image enhancement. That's what we have to understand today. So where we also going to define such a relationship of image enhancement in spatial domain. What is that is, what is gray level slicing? So what do you mean it? What does it mean it? So highlighting a specific range of gray levels in an image is called gray level slicing. So defining masking, that is the region of interest operations, is commonly called as masking. The mask is the small 2D array in which the values of mask coefficients determine the nature of processes. What is the image averaging? So we defining image averaging is nothing but a technique that it is often employed to enhance video images that have been corrupted by random noise. So, what are the application of an image enhancement? Here are some example of image enhancement. Number one, blur image. Number two, contrast adjustment of an image. Brighten, that is brightness of an image, and smooth and sharpening of an image, which are under the image enhancement, especially in the spatial domain. That what we are understanding about some of the examples of image enhancement. I am repeating here: blur image, that is a blurred image. If we are keeping into in terms of deblurred images, contrast adjustment, brightness, that is brighten an image. Next, smooth and sharpen. Let us we have to understand the terminology about smoothing. The meaning of smoothing is here. Image smoothing is a digital image processing technique that reduces and suppresses an image noises. Commonly seen smoothing filters include average smoothing, Gaussian smoothing, and adaptive smoothing. Here, image sharpening filters highlighted edges by removing blur. So that is noise removal. Noises are introduced to images at the point of capture from cameras, printing, or during transmission. In terms of image processing, noises can be identified with a variance of intensity from its neighbor pixels. So I am repeating here how we concentrate such a simple meaning of noise removal is noises are introduced to image at the point of capture from the cameras while printing an image or during transmission from one device to the other device of image transmission. We may going to be concentrate on noise removal. Whereas in terms of image processing, noises can be identified with a variance of intensity from its neighbor pixels. That is very simple. Let me go in detail about such a various types of noises are here. There are the various noises which we are having here. For example, the Gaussian noise changes each pixel by a small amount, and salt and pepper noise, impulse noise. Those are impulse noise. Randomly scatters white or black pixels over the image. So noise removal techniques reduce the visibility of noises by smoothing the image using linear or non-linear filters. Grayscale image histogram equalizations. That is, histogram equalizations refers to the transformation where an output image has approximately the same number of pixels at each gray level. That is, the histogram of the output is uniformly distributed. So where we are going to be simply have the definition about image histogram equalization means histogram equalization refers to the transformation where an output of an image has approximately the same number of pixels at each gray level. That will do the major job of the histogram of the output is uniformly distributed. That is what we have to understand from here. And we extend about this image enhancement techniques if you want to not only having a simple definitions and terminologies, but we have to concentrate that image enhancement techniques. We are how we may be extend our knowledge about this image enhancement techniques by defining or by knowing how many types of image enhancement techniques. So here the image enhancement techniques which we are going to keep based on taking an input and getting an output of the image, which we are going to be have the two types of image enhancement techniques. Number one, spatial domain technique. Number two, frequency domain technique. The manipulated pixel intensity directly is called spatial domain technique. Whereas frequency domain techniques is also concentrate the modify the Fourier transformation is called frequency domain technique. But compared to 1 and 2, where spatial domain technique simply we concentrate on intensity directly, but here we are going to use the frequency domain technique in terms of Fourier transformation for search. There are the two major types of image enhancement techniques. Let us we take one example to understand such a difference in between spatial domain and frequency domain. Frequency domain. Spatial domain is, let us we take that the image which is here, the linen image, which is right now we apply the transformation, Fourier transformation. Such a image, okay, such a linear image which we are concentrating to transform in terms of frequency domain. This is standard image which we called simply we says that a standard image where we keeping in lady image we called simply Lena image. So this image which we keeping in terms of spatial domain nothing but black and white as a grayscale image transform into for frequency domain. How we can transform? By the help of Fourier transform domain or by the help of Fourier transform method. Then we will get your output of an image. Let me have the second part of such a spatial domain which we are keeping on to know based on the basics of spatial filtering which we are going to use in the image enhancement. So what does it mean these filters in spatial domain? How we may be define it? Simply we says that spatial filters used different marks, nothing but kernels, templates or windows. These are one-to-one correspondence between linear spatial filters and filters in frequency domains. Where these spatial filters and filters in frequency domains are considered in between linear spatial filters and filters in frequency domain. If suppose we consider spatial filters can be used for linear and non-linear filtering. Frequency domain filters must just for linear filtering. That's what we get to understand in detail. The mechanism of spatial filtering is spatial filters consists of either two. Number one, neighborhood, that is called a small rectangle filtering. Number two, predefined operation that is performed on the image pixel. Predefined operations that is performed on image pixels. The filtering creates new pixel with the coordinates equal to the coordinates of the center of the neighborhood and whose value is the result of the filtering operation. So let us we have the in detail about the spatial filtering technique is used directly on pixels of an image. The mask is usually considered to be added in the mask is usually considered to be added in size so that it has specific center pixel, which we defining in terms of spatial filtering. I'll repeat, the meaning of spatial filtering is a technique used directly on pixels of an image. That is simply usually considered a mask is added in size so that it has a specific center pixel. Here we are going to be see that this mask is moved on the image such that the center of the mask traverses all images pixels. Why? Because we are keeping it added in size so that it has specific center pixel towards to mask traverses all image pixels. Then how we may be classify such a basis of linearity? There are two types of spatial filter linearities. Number one, simply we say linear spatial filter. Number two, non-linear spatial filter. There is a question is here. On what basis of you are going to be classify such a basis of linearity in terms of spatial domain. Very simple to understand a image which we are keeping, in terms of filtering process. This filtering process, which we are keeping in between the relationship of input and output. This relation may have the in terms of linear relation, or number two, non-linear relation. What do you mean linear and non-linear relation? Linear means the output of filtering process always follows the input, is called linear. Whereas non-linear filtering process is called the output of the filtering process 100% follows the input. So this is what we want to understand, the difference between linear spatial filtering and non-linear spatial filtering. So, if the operation performed on the image pixel is linear, then the filtering is called a linear spatial filter. Otherwise, the filter is non-linear. I repeat once again the definition of such a classification of linear and non-linear spatial filter. Simply, we says that the operation performed on the image pixels is linear, then the filter is called linear spatial filter. Otherwise the filter is called non-linear. Below figure, that is what we are going to show right now, represent in terms of understanding the mechanism of linear spatial filtering in terms of using 3 by 3 neighborhood pixel matrices. The response of output, which we represent in terms of g of x comma y of the filter at any point of x comma y, is we are going to represent in this figure. So let us take, this is the origin of the origin, that is original image which we keeping in terms of image of spatial domain. The meaning of spatial domain means you are represent the x comma y coordinates. That x comma y coordinates which are varying the relationship of one value to the other value, how it is varying in terms of 3 by 3 neighborhoods of the pixel comma, which are represented in terms of x comma y, called image of spatial domain. So here, you suppose you take this having relation x comma y, it is having relation, this is y axis, this is x axis of the coordinate. So this is may having that relation. So suppose you wanted to have that in the image is the sum of products of filtering coefficients and the image pixels values represent in terms of g of x comma y. That is window -1 comma -1, that is what we are concentrating one by another, is here we represent window and as well as your pixels of the neighborhood represents. Okay. So by the summing all together, that is sum of products of filtering coefficients, is we'll get image pixels values as a image of spatial domain. So this spatial domain filtering observed that the center coefficient of the filter is window of x 0 comma 0 aligns with the pixel at the location x comma y. Very generally, mask of the such a image of an spatial domain is represented in terms of matrix m comma m into n, where m is that size which we defined in terms of 2a plus 1 and 2b plus 1, where a comma b are the positive integers which are help us to define the filtering process in terms of general mask of size. But where odd filters are also will define in general linear spatial filtering of an image of size capital M into small n with a filter of size m into n is given by expression g of x comma y is equal to summation s equal to minus a to small a minus b to small b, and w x comma y is window, and f of x plus s and y plus t are represented in terms of your x or y are varied, that the pixels, each pixel in the window in w, that is image of the spatial domain, visits every pixels of the object function of f. where f is represented in terms of x comma y. This x and y will be changes instead of x as x plus y else and y plus t. This is what we are going to keep in terms of linear filtering processes. Where we understand such a theory in terms of filtering mask is we are consider mask means the central pixel of the represented output value is mask. So filtering mask is started from center. So from this we are represent your Windows filter coefficients of the values and the pixels of image section and filter. The spatial correlation and convolution both will represent in terms of image pixels values only, which we can understand from the figure 1. Of course, we understand so far how we define such a spatial filtering by the help of masking of an image processing. But functionality of mask, how we may define is the functionality of the mask is called masking is an image processing method in which we define a small image piece and use it to modify a larger image. Masking is the process that is underneath many types of image processing, including edge detection, motion detection, and noise reduction. So, a mask is a binary image consisting of 0 and non-zero values. If a mask is applied to another binary or to a grayscale image of the same size, all pixels which are 0 in the mask are set to 0 in the output image. So where the usage of such a mask for blurring image in this process, blurring we reduce the edge content in an image and try to make the transition between different pixels intensities as smooth as possible. Noise reduction is also possible with the help of blurring. The forcing or faking eye contact during conversations, imitating smiles and other facial expressions, mimicking gestures, that is, hiding or minimizing personal interests, developing a repertoires of rehearsed responses to the questions. The general classification about this spatial filtering, which we are understanding from the type of spatial filtering is that is smoothing spatial filtering. Smoothing filtering is used for blurring and noise reduction in the image. Blurring is a pre-processing steps for removal of all details and noise reduction is accomplished by blurring. The types of smoothing spatial domain, that is spatial filtering, is represented in terms of linear filtering means mean filtering, and number 2 represent order statistics, nothing but non-linear filtering process. Define mean filter, that is linear spatial filtering is simply the average of the pixels contained in the neighborhood of the filter mask. The idea is replacing the value of every pixel in an image by the average of the gray levels in the neighborhood defined by the filter mask itself. That is multiplied by a higher value than average filter is to define in terms of types of mean filter. What are the types of mean filter? If we have that such a definition, so there are two types of mean filter. Number one, averaging filter, that is used in reduction of the detailed, that is detail in image. All coefficients are equal. Number two, weighted averaging filter. In this, pixels are multiplied by different coefficients. There, the center pixel is multiplied by a higher value than average filter process. So what does it mean this order statistics filter is here? Simply we define based on the ordering of the pixels contained in an image area encompassed by the filter. It replaces the value of the center pixel with the value determined by the ranking result. That is, edges are better preserved in this filtering. That we can understand a simple definition about order statistics filter. And we also extend this order statistic filter to understand how many types of order statistic filters are. There are two. What are those? Number one, minimum filter. Number two, maximum filter. If you want to define such a minimum filter, 0th percentile filter is the minimum filter. The value of the center is replaced by smallest value in the window. Is minimum filter. Whereas maximum filter, we used to say 100%, that we called as 100th percentile filter is the maximum filter. The value of the center is replaced by the largest value in the window is called the maximum filter. Whereas third one, which we missed, the types of filtering here is three. Number one, what we call minimum, maximum, and median filter. Each pixel in the image is considered. First, neighboring pixels are shorted, and the original values of the pixels is replaced by the median of the list. Sharpening spatial filter, it is also known as the derivative filter. The main purpose of the sharpening spatial filter is just the opposite of the smoothing spatial filtering. It is main focus on the removal of blurring and lighting the edges. It is based on the first and second order derivative. The first order derivative of the spatial filtering simple we says that that is we define in a simple way must be zero in the flat sequence, must be non-zero at the onset of a gray level step, must be non-zero along ramps. These are the first order derivative which we are achieving in terms of 1D as a defined equation, that is f dash equal to f of x plus 1 minus f of x is the formula of first order derivative spatial. The second order derivative, which is simply we also repeat the same, must be zero in flat areas, must be zero at the onset and the end of ramp, and must be zero along ramps. Second order derivative in one dimensional is given by f double dash is second order equal to f of x plus 1 plus f of x minus 2 of x is the second order derivative for the one dimensional given image. I hope you understood today the complete definition support image enhancement and the basic spatial filters, which are simply we define with the simple definitions, which are more important in terms of definition and terminology. I hope you understood each and every definition and technologies. I'm very thankful for your understanding. I'm also extend my cooperation to you and says one important point. You can refer the textbooks which we want to understand much more on the same definition and technologies. With this, I want to close today's session. I'm very thankful for your understanding these concepts. So thank you so much. Thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.